So if we want to be able to describe a sequence in terms of previous values along the sequence, we can use a method called recursion. That is, we can come up with our recursive definition, or our recursion formula, or recurrence relation. There are a bunch of different names for this type of idea, but basically what we do is we use previous values, previous terms, to get our next one. So for example, with the Fibonacci numbers, we could, instead of using that nasty, explicit general term formula, well, we just say that Fn, the nth Fibonacci number, is equal to the n minus first plus the n minus second. That is, Fn equals Fn minus 1 plus Fn minus 2. A lot simpler that way. And it makes sense if you think about it that way, because you think in terms of rabbits, we get the nth number of rabbits by looking at the amount from the last two counts, because those last two counts get us all the way up there, where it is important to know that when we have these things, we also need values called initial conditions, where we need the same number of initial conditions as we have previous terms in our recursion definition. So in this case, we would specifically need to say that F1 is equal to 0 and F2 is equal to 1. But if we have those conditions and we have that definition, we can then get any value in the sequence, provided we have all of the ones up to it. So it sometimes takes a little bit more work, but it does help us get some pieces in certain cases. And we're going to look at an example for how we can do this next. So for this example, we want to find the first four terms in the sequence in which a1 is equal to 1 and an is equal to an minus 1 over 3. So again, notice here that we have our initial condition that a1 is equal to 1, and then we're told something about an in terms of the one before it, an minus 1. This is a recurrence relation, as it were. So if we want to find a1, well, that's the one that we're given initially. We need that one to start. We get that a1 is equal to 1. And then from there, if we want to get a2, we look at the one before a2, which is a1, and divide that by 3. So we just get 1/3. Then for a3, we take the one before a3, which is a2, and divide by 3, which would give us 1 over 9. And then finally for a4, we would take a3, divide that by 3, and get 1 over 27. Where, again, the weakness of recurrence relations is that we need all of the terms to be able to get to the next one. And often in combinatorics, that is the math of counting, discrete math is another sort of thing you talk about with combinatorics, you want to take something like this and be able to turn it into a general term formula, something closed. I can just tell you if I plug in n, I get out the value for an. In this case, if you're paying attention, you should be able to tell that an is going to follow the pattern 3 to the 1 minus n, or if you prefer, you could flip those around, throw in a 1/3 in there, say it's 1/3 to the n minus 1. It's another one of those geometric type things, but we could get a closed formula there if we wanted to. It's pretty easy to see the pattern, although I will say it's, well, not always the very simplest thing to go in that direction, and see what I talked about with the Fibonacci numbers if you want some proof of that. But hopefully some of you are looking at these things and thinking, well, hey, didn't we do something like this before? And we have done something like this before. We just didn't really call it recursion. Because if you think back to when we were talking about matrices, we were looking at trying to get the determinant of some n by n matrix. We always expanded by minors. And when we were expanding by minors, we always took that big piece, like a 3x3 or a 4x4 or a 5x5, and broke it down along a column or row to get down a selection of smaller matrices. And even though we didn't call it recursion, that actually is another form of recursion, where any sort of pattern that involves taking a big piece and breaking it into a series, or maybe just one smaller piece that we know more about, is a recursive process. It's the sort of process that computers run really well on, actually. But anyway, the next thing we're going to see here is a bit that also can work nicely with recursion, called factorials, which are things that anyone who has taken stats before should have some familiarity with.